If we generalize lines and planes, add a little bend to them, the idea of a line will generalize to curves. Now, curves, we're going to have to parameterize these. And this is a little bit more complicated than we want to get into right now. We're going to hold off until chapter 12 to talk about curves. If you take the concept of a plane and you throw a little bend in there, you get the idea of a surface. Now, surfaces we're going to talk about in this section. There are three convenient types of surfaces to discuss. The first is the idea of a cylinder. Now, a cylinder starts out as a function of one variable. So say y equals sine x. So the function y equals sine x, we can graph this using regular calc techniques. So you see this graph here, sine starts out at 0. There's one period displayed on the right-hand side and one period on the left. Although sine is periodic, so you see this is going to repeat. Now, y and x are the only variables in here. So if you were to take this, think of the z-axis as coming out of the screen. We're going to take this, every point we have along the sine curve, we're going to extend it out of the screen and into the screen at the same time. And that's going to give us a picture that looks like this. We've got still the sine curve on the right, the sine curve on the left, although at every point we've got this line that heads in and out of the screen. So that's the concept of a cylinder. It's a function of two variables. The third variable is free. So it just gives us this is the cross section. The second type is a generalization of the idea of a conic section. So conic sections, if you recall, you had three basic types of these. You had the ellipse, the hyperbola, and the parabola. These generalize to something called quadric surfaces. A quadric surface is essentially a conic section with three variables. Now there's a list of these in your book in chapter 11.6. We're going to look at a method for graphing one of these right now, and we'll see if this is enough to go on. Let's say we've got the function z equals 9 minus x squared minus y squared. So the method that we're going to use for graphing this is called the method of level sets. So what we're going to do here is look at what happens when z is constant. So if we were to hold z constant, well, let's look at some specific z values. If we plug in z equals 0, you plug 0 into this, you move the x and the y over, and you've got x squared plus y squared equals 9. So that says at height 0, so here's my x, my y, and z. At height 0, in the xy plane, we have a circle of radius 3 in the xy plane. Well, let's look at what happens with some other z values. Just for convenience sake, I'm going to plug in z equals 5. If you plug in z equals 5 here, we move some stuff over, we get x squared plus y squared equals 4. That's as if we go up 5 units. Up here, we have a slightly smaller circle, a circle of radius 2. If we plug in z equals 8, we get x squared plus y squared equals 1. So up here at 8, we have a smaller circle. And then if you look at z equals 9, we've got x squared plus y squared equals 0. This is a degenerate circle, a single point. So if you look at this, this naturally suggests maybe some sort of dome shape. We'll see an actual professional graph of this in a second. So we should have this, we have a bunch of circles. The circles get smaller as we go up the z-axis, they get bigger as we go down the z-axis. And that gives us this picture right here. And this is called an elliptic paraboloid. We call it elliptic because each of these cross sections look like ellipses or circles. And we call it a paraboloid because if we look at along the xy direction, it looks like a parabola. And along the along the yz, it looks like a parabola, and along the xz, it also looks like a parabola. So if we were to slice this with a plane coming down, we would get parabolas. A plane coming across, we get ellipses. So that's where the term elliptic paraboloid comes in. And the last type we're going to talk about is the idea of a surface of revolution. So a surface of revolution, there are three types of these depending on which axis you're going to revolve around. A surface of revolution should look something like a function of x equals y squared plus z squared, or a function of y looks like x squared plus z squared, or a function of z looks like x squared plus y squared. Okay, this first one represents a curve that's been revolved around the x-axis. The second one represents one that's revolved around the y-axis, and the third one is one that's revolved around the z-axis. Let's take an example of this. So let's say we've got the function y equals 1 over x. So if you look at 1 over x, just a small slice of this, we've got this standard hyperbola graph, the hyperbola shape. And now what we're going to do is we're going to take that picture and we're going to revolve it or rotate it about the x-axis. So rotating about the x-axis, well, that means we've got to hold these x's sort of by themselves. We have to isolate all the x's. This is going to be our function of x. So I see that my radius, when I rotate this around the axis, my radius will be 1 over x. So if I square both sides, I get r squared equals 1 over x squared. Now this r squared is the distance from a point on the curve to the x-axis. And that can be represented from the x-axis by y squared plus z squared equals 1 over x squared. So this gives us the surface of revolution generated by rotating this about the x-axis. And graphically what that looks like is this picture right here. We've taken the 1 over x, we've taken that 1 over x and we've spun it around the x-axis, and that gives us this shape right here. If we were to take this and say rotate about, say, the y-axis. Okay, this is going to be a little trickier. So we're going to take this curve, rotate it around the y-axis. Well, I want to have y by itself. So if I isolate all the y's, well, this is already isolated for y. So that says that my y value, now this x is representing the distance from the axis. So that's 1 over r. Now I want to square this so I can use that same identity from polar. So I know that y squared is 1 over r squared. And we can replace this. We can write it as y squared equals 1 over x squared plus z squared. Because again, the distance from the y-axis is the square root of x squared plus z squared. And so this would be our curve if we revolved it around the y-axis. So those are the three basic types of surfaces that we're concerned with. And we'll get a chance to see many examples of these.